Good morning, this is Course 9 of Meettechniek 2013-2014. This is Edwin Carlin giving the lecture this last year for the University of Twente in the Netherlands. And I'm giving a video from the University of Tsukuba in Japan. Today's lecture on January 6th, 2014, I will talk about pressure measurement and flow measurement. So today we're not going to be talking about electrons or typical electrical engineering topics. I'm going to be talking about hydraulics and pneumatics, and these are quite important topics even for electrical engineers, especially as electrical engineers apply control systems for different applications. But interestingly enough, many of the fundamental assumptions that we make about circuit analysis, such as Ohm's law and Kirchhoff's voltage and current laws, interestingly enough, came from the analysis of hydraulic systems. So you'll see a direct relationship to the equations that we use in general to analyze simple circuits, hydraulic and pneumatic circuits. As a reminder, homework number 8 is due today, and homework number 9, the last homework for Meettechniek this semester, is available on Blackboard. Also, I want to remind you that homework number 9 is due on Monday, January 13th. And the solutions will be available on Tuesday, 14 January. So make sure if you're going to hand in homework number 9 that you hand it in on time, because the solutions will be available that following Tuesday so that you'll have them in order to be able to study for the final exam. Also a reminder that the final exam is on the 20th of January, and you can find the details for the location, the university administration. First, I will make some definitions, pressure definitions. For a fluid at rest, pressure can be defined as the force exerted perpendicularly on a unit area of a boundary surface. So we know that pressure in general can be defined as force per unit area. Therefore, its units are going to be force per unit area, Newton per meter square in SI units. So pressure is basically a mechanical concept that can be fully described in terms of primary dimensions: mass, length, and time. So we have Newton and meter square. So Newton, then we get mass, length, and time involved, and then the area, we also have length involved. Interestingly, pressure is not affected by the shape of the confining boundaries. Thus, a great variety of pressure sensors can be designed without concern for shape or dimensions. And in case you don't know it, because we are dealing also with pneumatic systems, the kinetic theory of gases states that pressure can be viewed as a measure of the total kinetic energy of the molecules. So the pressure is equal to 1/3 rho, and then we have this funny term, velocity in a bracket squared, okay? And these brackets are essentially time averages, because we deal with ensembles, large ensembles of gas molecules. And then that can be also defined as n RT. Or in other terms, we can say that PV, in this case V is volume, is equal to N RT. And this is the ideal gas law that states that the pressure times the volume is equal to these constants. N is the number of moles of gas in the in the volume. R is a constant, and then T is the temperature. So this is quite convenient if we're dealing with pneumatic systems, that we can use the ideal gas law. In reality, this law does not strictly hold. This law assumes that the molecules in the gas are not interacting with one another, when in reality they are. So there are some corrections to this general ideal gas law that can be applied. But for this class, we will assume that we can use the ideal gas law for analyzing pressure and volume. For pressure measurement, some definitions that you may not be familiar with. Overpressure, so this is a pressure above ambient pressure, which is 1 atmosphere. If you're in outer space, then ambient pressure is much, much different. If you're in a vacuum chamber, then your ambient temperature pressure is much, much different. Vacuum is some pressure below the ambient pressure. Absolute pressure, the difference between the fluid pressure and the absolute zero of pressure. Gauge pressure is something that you read from, literally from a gauge, and then absolute pressure is gauge pressure plus atmospheric pressure. And then the differential pressure, that we typically call delta P, is the difference between two absolute pressure values. Pressure units. There are many pressure units. Unfortunately, there is no real standard on which pressure unit is used between different engineering fields, or even if you want to buy pumps from different companies, they specify in different units of pressure. But the standard SI unit of pressure is a Pascal, PA, which has Newton units of Newton per meter squared. And the definition of the standard atmosphere is 1 ATM, which is 101,325 pascals exactly. And then in the table below, on slide 4, we have some units. So we have bar, millimeters of mercury, inches of mercury, torr, pounds per square inch. There are many, many more. These are the most common. So be careful which units you're using and how you're defining pressure. So one of the most common ways to measure a pressure difference, both pneumatically and hydraulically, is with the use of a diaphragm. And the diaphragm will have different pressures between the bottom and the top of the diaphragm, which causes a deflection, and then we typically measure a deflection of a diaphragm. So in pressure sensors, the sensing element is a mechanical device that undergoes structural changes due to strain, and the strain comes from the fact that the pressure, a difference across this mechanical element, is going to cause some movement. So historically, such devices were Borden tubes and many different types of funny things. Pressure is one of the oldest measurements throughout history, because of the importance of water and these types of things for not only just for consumption, but also for sailing and these types of things, also for merchants and these types of things. A popular example of pressure conversion into a linear diffraction is a diaphragm, as I said. Aneroid barometer, for example, that's located on the bottom. So a deflecting device always forms at least one wall of a pressure chamber and is coupled to a strain sensor, for example, a strain gauge, which converts deflection into electrical signals. So the device located on the bottom has a diaphragm that's located in the center of this box. On the top, you have a particular pressure, which is in gray. On the bottom, you have another pressure that's maintained at some pressure. And this diaphragm is fixed or anchored to the walls of this vessel. And when you get an increase in pressure P, but you do not get an increase in pressure on the lower white area of the vessel, then this diaphragm will bend downwards because you get a net force pushing, force per unit area pushing on this diaphragm. And then as the diaphragm pushes down, it creates more strain in the strain sensor. Therefore, you change the electrical resistance, you get a current change, and then you can measure the current change via the amplifier that's shown. When one pressure is applied to one side of a diaphragm, it deforms, as I said. Diaphragms can be plates, which is located on the top, or membranes on the bottom. And although these look almost identical, the way that they bend and the pressure ranges that they're used, very, very different. So on the top, you'll see that the plate is typically thicker, and you'll notice that the way that the plate bends is much, much different. So you'll see at the edges where it's anchored, you'll see that we get a bending moment in the plate, which means that the plate is straight as it connects into the wall, but then it bends and it has a clear moment, a bending moment in the plate. Now, membranes, the definition of membrane is it's typically very, very thin, and you'll notice that the anchor point onto the wall, at both the left and the right of the lower plot in B, that the membrane does not have a bending moment. It just bends right at the interface with the wall. So the dynamics of the bending is very, very different, and therefore the displacement that you have is very different. So the displacement as a function of pressure is going to be very different. So you have to be quite careful in whether you use a plate equation or a membrane equation in order to relate the deflection of a membrane in the center with respect to the pressure. So for membranes, we typically look at the center deflection, and the center deflection and stress has the same units as the pressure, are quasi-linear functions of pressure, which means that over a short range or over a finite range, you can get a linear function of pressure, the center deflection. But only over a finite small region is it going to be linear, and it can very quickly become nonlinear, so you have to be careful with this. Now, it is a thin diaphragm under radial tension that has units Newton per meter. Now, notice that this radial tension is different than tension that you probably saw in your physics courses, tension on a rope, okay? So this is radial tension in the membrane. Now, the stiffness of bending forces can be neglected in this case, as the thickness of the membrane is much smaller than the radius, typically 200 times. It can be greater than that. Okay. Now, the center deflection over this quasi-linear range can then be written as r squared times the pressure, P, divided by 4 times the tension. And then the maximum stress is T over G, where G is the thickness of the plate, the membrane. Now, plates, on the other hand, the thickness is not negligibly small. Okay, so we can't use the same assumption that we had last time in the case of membranes. Now, when pressure is applied to one side of the plate, as we had in the membranes, then it deforms. At low pressure differences, the center deflection and the stress in the plate are also quasi-linear functions of pressure. However, now we have to include material properties because the plate is a bit thicker than the membrane case. And so we have to include material properties. E is the Young modulus. And nu, 1 minus nu in this case, is a property of how the plate bends. It's a mechanical property, it's a material property, and it is a function of the bending properties across an area, okay? And then the maximum stress is about 3 times the radius squared multiplied by P divided by 4 times G squared, and G is the thickness. Now, to make a pressure sensor, 2 essential components are required. We either have a plate or a membrane having a known area and a detector which responds to the applied force. So common methods are piezoresistive, capacitive, and variable reluctance. All of these things we've seen in the past, and we've analyzed some circuits. And now we're going to apply them to pressure sensors. Okay, so a piezoresistive readout, when stress is applied to a semiconductor, in this case, let's say silicon, a resistor, having initial resistance R, the piezoresistive effect results in a change in the resistance, delta R. Now, we saw this example in an earlier lecture where we have a top view of the pressure sensor located on the top picture on the left, and we have a cross-section of the pressure sensor located on the image on the bottom. So let's look at the top view first, and you see that we have 2 squares. We have a dark gray square on the outer ring and a light gray square on the inner ring. So the dark gray square is the platform, and the light gray area is a square diaphragm of constant thickness. Okay, in this case, we're going to assume that this is a plate. So the thickness of the diaphragm we can see on the lower diagram, where we have, if we look at just the top part, we're going to have these thick regions on both the right and the left side, and in the center we have a thin diaphragm. So this thin diaphragm region corresponds to the light gray region in the top image. Now, when we get a pressure, this square diaphragm is going to bend, and it's going to have the gray deflection directly in the center of the square diaphragm. Now, in order to detect that deflection, we use 2 resistors, and these resistors are made from the silicon, but they're made in a way that we implant impurities, boron, phosphorus, arsenic, in a controlled region, and we make a resistor. So you know that silicon is a semiconductor, and when we add dopants, we can increase the conductivity. So in these regions, R1 and R2, we add impurities. Let's say that we add boron, okay? And in those regions, then, we can make a pretty good resistor. And this resistor then becomes a piezoresistor because it's made of silicon, and we know that silicon can be a piezoresistive material. And so now we have these resistors defined, and you see that they have a specific orientation. In R1, the length extends down the center of the diaphragm, and R2 extends the width is in the direction towards the center, and the length is on the edge. So in this case, if a pressure is applied to the top of the pressure sensor, which is greater than the pressure in the cavity, which is you can see on the bottom image, then the membrane or the plate is going to deflect down. In this case, R1 is going to stretch. And when it stretches, then you're going to change the resistance. At the same time, now R1 is the length is stretching, so you're going to get a certain resistance change. Now R2, interestingly, the width of R2 now is going to stretch, not the length, but the width. Now, because silicon is a crystalline material, the resistance changes between the length of the resistor and the width of the resistor are going to be differently because it's a crystalline material. And so the equation on the top, delta R over R, is the contribution of two components, a longitudinal component, which would be in the x direction, and a component, which would be in the y direction. Okay, so then we can say that for both of these cases, for silicon, we can say both of these, the longitudinal and the transverse coordinates, we have these pi L and pi T. We're going to assume for silicon, and it's a pretty good assumption, that it's equal to 1/2 pi 4, which is a constant of the material. Then we can go and make changes in the resistance. Delta R1 over R1 is equal to minus delta R2 over R2, which is equal to 1/2 pi 44. But then we have the stresses, 1x and 1y, because these are stretching in different directions. So then the V out from our sensor is just going to be V in, 1 over 4, pi 44, times sigma 1y minus sigma 1x. Okay, now we can process this further, but essentially this pi 1 or the sigma 1y and sigma 1x, we can process these later to be a function of the pressure that's applied, but it's not necessary. So remember from the previous calculations that we had relationships for the stress in the membrane as a function of pressure. So in reality, the transfer function here, V out, is a function of these stresses, and these stresses are a function of the pressure. So this can be our transfer function. Now, what's interesting about these types of sensors is we can have 4 of them. We can make a full bridge. This is actually, we will probably have a homework problem on this, and then you'll have to work through putting these into a particular bridge configuration and thinking about how this relates to a particular type of bridge. Now we can also do a capacitive readout. Okay, now in a capacitive readout, it's easier to implement a capacitive readout. So these are basically, you have plates that are moving, and I won't show examples of these because I think you know how they work by now. And in this case, you would have a plate that's going to be moving, and you can still do a delta C type of measurement. The capacitive readout systems are interesting because they're a little bit easier to manufacture, and they can be integrated in an easier way with modern microcontrollers on the same chip. But a big difference between capacitive readout and piezoresistive readouts are shown in the two plots. And the capacitive readout is essentially nonlinear. The pressure versus center displacement is nonlinear. And with a piezo-resistive readout, it's very, very linear. The piezo-resistive also has a high temperature sensitivity that needs to be calibrated and compensated. So that's a drift in the system. But it shows you the two examples. So the capacitive is easier to integrate on chip, and to the processing of this is easier, but you have a nonlinear readout. Indeed, you can do calibration to compensate for this. And most of the modern highly integrated pressure sensors are made from these capacitors, but still a large number are made from this old technology using piezoresistive, because it's a pretty reliable technology. So in addition to that, the last one I will talk about today is a variable reluctance pressure sensor, and this is using the same concepts that we've been talking all along. So we have this magnetic flux flowing through this core material, and when you have a flat diaphragm, you set up a current, a magnetic flux in this system. When the diaphragm bends, you change the magnetic flux, so then you change the magnetic circuit, and then you can detect changes in the current flow. Or the EMF, or the coupling constant in the transformer, however you want to configure this. But essentially the material property changes, so you have this plate, and the plate had a particular reluctance associated with it. When you bend the plate, the gaps change, the length of distance that the magnetic field flows inside the core of the plate is different, so you can detect these changes. So all in all, the pressure sensors are pretty ubiquitous in industry, and it's a pretty well-developed field. And also miniature sensors made from silicon are still quite important. So in your professional careers, if you're dealing with measurement of any type of pressure or these types of things, then you'll become familiar with these miniature silicon-based sensors. I will move on to flow measurements. And now we're going to have to talk a little bit about some basics of hydraulics and pneumatics so that we're all talking in the same language. Also, these flow measurements you can read more in chapter 11 of the textbook. So flow measurement is concerned with quantifying the rate of flow of materials. And materials can be solids, liquids, gas. Mass flow rate is a mass of material that flows in 1 unit time, and a volume flow rate is a volume of material that flows in 1 unit time. So a mass flow rate would be kilograms per unit second, and a volume flow rate would be meter cubed in a unit second. So hydraulics deals with the properties of liquids, and pneumatics deals with the properties of compressed gases. So fluid mechanics is the science of dealing with all fluids, liquids, gases, plasmas, and the forces acting on them. And a variant of Navier-Stokes equation is used to describe the motion of fluid substances. Fluid flow systems have 3 basic building blocks consisting of volume flow rate, meter cubed per second, a flow network, and a pressure difference. So hydraulic, remember, fluid in an incompressible liquid, can't compress it. Pneumatic is fluid in a compressible gas, so gases can be compressed. So our quantities, volume V with a unit meter cubed. This is analogous to electrical charge. Pressure with a unit Pascal, which is equal to Newton per meter square. Is analogous to electric potential or voltage. Flow rate, phi sub V, and remember this is volume flow rate, meter cubed per second. And this is analogous to electrical current. Poiseuille's law, where we have the volumetric flow rate is equal to sigma sub V. This would be a conductivity times pressure. This is analogous to Ohm's law. Actually, this predates Ohm's law. Where Ohm's law originated was from some of the original estimations of flow rate based on the fluid, based on the geometry of flow channels and pressure differences. And then I show the conductivity in a small round container, and we'll talk a little bit more about this when we're calculating hydraulic resistances. So quantities in units of flow, flow velocity, meter per second. Now remember that flow velocity is a vector, and typically when we make measurements of flow speed, because we make measurements of a finite quantity. Mass flow, phi sub m, kilogram per second. Volume flow, phi sub v, meter cubed per second. And then we have these dynamic and kinematic viscosities, which are concepts of properties of a fluid that cause resistance to flow. And the unit of dynamic viscosity, A, which is Pascal second, and then kinematic viscosity is meter squared per second. So going back to the very basics of flow dynamics, we have to remember the thermodynamic law, conservation of mass. So if we use this and we say if there is an influx or an outflux of mass through the boundaries of a system, so in and out, the sum of the influx and efflux must be zero, conservation of mass. And we use this consistently in the field of fluid dynamics. When both influx and outflux or efflux are measured over the same time interval, then we can come up with this differential relationship. dm in over dt is equal to dm out over dt. Now moving media whose flow is measured are liquids, water, oil, solvents, gasoline, etc. Air, gases can be oxygen, nitrogen, carbon monoxide, carbon dioxide, methane, water vapor, etc. So flow dynamics. In a steady flow, the velocity at a given point is constant in time. Therefore, no acceleration. So we can draw a streamline through every point in a moving media. A velocity vector is tangent to a streamline in every point z. And an example is shown on the bottom. Okay. So the flowing media can enter such a pipe at one end, having cross-section A1, and exit at the other through a cross-section A2. This is called a tube of flow. The volume of moving media passing a given plane in a specified time interval dt, then this phi sub v, which is our volume flow, is going to be whatever volume is passing that plane unit time, which is then the volume can be written as delta x over some differential area over the same delta unit time. Which then can be written as a velocity times this differential area. Okay, now we have to be careful here when we talk about quantifying the flow rate based on this velocity through a unit area. Okay, the figure on the left, this shows a velocity flow profile of a liquid between two boundaries, these hashed boundaries on the upper and lower. So this is a pressure-driven flow, and you can see that the velocity is not constant. The velocity is very low at the walls and maximum in the center. So when we're talking about the flow velocity, we're always dealing with an average flow velocity. Okay, so we're going to average it over the length, the height of the tube in which we're measuring it. So V sub A, this average is going to be we have this integral of the velocity times the differential of A over the total cross-sectional area. This will give us an average velocity and not a precise estimation of velocity, because you can see that we have a profile of velocities depending on the liquid and how the liquid interacts with the surface of the boundary. So we have to be careful. Now when we measure the flow velocity by a sensor whose dimensions are very, very small, so if we have a pipe and we put a little sensor on the base of the pipe and we measure a flow speed, then we're measuring a flow speed that's typically much, much smaller than the flow speed at the center. So we have to use a full characterization of the system so that we get a good estimation of what the velocity is in the profile. A product of the average velocity cross-sectional area is called the volumetric flow rate. A flow sensor usually measures VA, this average velocity, and thus to determine the flow rate, the cross-sectional area of the tube must be known in this case. Now viscosity. Viscosity is a measure of a fluid's resistance to flow. High viscosity doesn't like to flow. Low viscosity will flow. Viscosity can be measured and reported as dynamic, which is absolute viscosity, or kinematic. And we have different quantities and units. So dynamic viscosity is in Pascal seconds, or poise, and kinematic viscosity is in centimeter square per second, or a Stokes. And then a Newtonian fluid can be described as a fluid that maintains constant viscosities across all shear rates. So that means that the flow rate of the system is basically, the shear stress in this is going to vary linearly with shear rate. And non-Newtonian fluids, they don't behave in this way. They don't have a constant viscosity. So in this class, and in most cases, our fluids will have a constant viscosity, and we can assume that they are Newtonian fluids. So hydraulic elements, now we can relate to components, the lumped modeling approach, a capacitance, which is meter square, and this is typically energy storage within a liquid in the form of a potential energy. This is a height of liquid in a container called a pressure head, is one such form of storage. So CV in this case would be the delta volume over delta H. Now remember that if you see in the picture here, we have a container that has a certain cross-sectional area A and a certain height. Now the pressure that's exerted by that head of fluid with height H is going to be rho GH. Pressure is going to be rho GH. Rho is a density, G is the gravitational acceleration, H is the height of this volume of liquid. So CV then is going to be A divided by rho G. Now, interestingly enough, we can use our differential equations, and we can say that the pressure then is equal to 1 over CV, and the integral of the flow rates of V1 phi of V1, the flow rate going in, minus, the typo here, phi V2 dt. This is very similar to a capacitor, right? Where we have current I is equal to C, C is equal to dV dt. In this case, P is analogous to voltage, so we can use the same relationships in order to solve these differential equations, and we'll do an example of this. So delta V in this case is change in volume, meter cubed, and delta H is in head height. And head height is just the height of the volume of fluid, H. And in the energy storage, we can use the same type of relationships. For an electrical system, we had 1/2 CV squared. For a hydraulic system, it's 1/2 CV, the pressure difference in the system between P1 and P2 squared. Inertance, this is equivalent to inductance in electrical systems. It has unit meter squared. Now, to accelerate a fluid and to increase its velocity, a force is required. Okay. Now, interestingly enough, we can use the same relationships that we have for an inductor to estimate the volumetric flow rate due to inertance, I sub V. Hydraulic resistance, Pascal second per meter cubed. This is the resistance to fluid flow, which occurs as a result of liquid flowing through valves or changes in a pipe diameter. And the hydraulic resistance then is very similar to Ohm's law, which is delta P over the flow, and this would be then V is equal to IR, the same type of relationship. Now this becomes important when we use the Poiseuille equation, and this physical law, as we saw earlier, gives the pressure drop, delta P, in a fluid flowing through a long pipe. Now we have to be a little careful here in that our assumption is that we have what's called laminar flow, viscous and incompressible. And to be laminar, then, we have something called the Reynolds number that we have to calculate. To be laminar, then, this Reynolds number has to be lower than about 2,000. And then we can use these nice relationships similar to Ohm's law. What happens is that if we have Reynolds numbers that are quite high, then the flow becomes turbulent. And it's quite chaotic, and we can't use these well-behaved equations to estimate the hydraulic resistance. But I have to say that in the area of miniaturized flow systems, the flow is usually laminar. Okay, so this is not a in big tubes, big pipes, flow can be turbulent quite often, so you have to be a bit more careful. Now, the resistance, hydraulic resistance, is highly dependent on the shape of the channel. So this is a slide that shows the hydraulic resistance expression in the third column. And you can see that we have 6 different shapes here. The top is circle. So the hydraulic resistance expression that we saw earlier is this top expression, 8 over pi times eta L over 1 over a to the fourth. It is the radius of the tube. Now if we have an ellipse or a triangle or just 2 plates or a rectangle or a square, the hydraulic resistance factor for laminar flow is quite different. So you have to be a little careful when you're calculating these systems to know what the approximate shape of the hydraulic channel in order to be able to estimate the hydraulic resistance. Okay, so those are the 3 basic components. Now we can do an example of using lumped modeling, using our capacitance, our inertance, and our resistance, and Ohm's law, and also the equations of the differential change of the pressure and flow and capacitance and also the inertance. So consider a simple hydraulic system, as we saw in a previous slide, where liquid enters with a flow rate phi sub V1 and leaves the container on the bottom phi sub V2. Such a system can be considered to consist of a capacitor due to the liquid in the container and a resistor due to the exit valve. Inertance may be neglected because the flow rate changes very slowly. Okay, so if we have an electrical system, we have R, L's, and C's. In this case, we're going to get rid of L, and we just have an RC circuit. So let's find an expression for the height of the liquid, H, as a function of the inlet flow rate, phi sub V, and outlet flow rate, phi sub V2. Okay, we're going to use the same expressions that we derived for the elements. So we know that the difference of the flow rates is going to be C, V, dp dt. So then the pressure, we can rearrange this. Now for the resistance, we're going to use Ohm's law, which is delta P over phi sub V2. And then we know that the pressure delta P is simply going to be the pressure head due to the liquid in this container, which I said earlier is rho gh, density times the gravitational acceleration times h. Now what we find in this problem is h. How is h changing in time due to these two flow rates? So you can imagine if phi sub v1 is much, much larger than phi sub v2, then this thing is going to continue to fill up. If phi sub v2 is much larger than phi sub v1, then this thing is going to empty, and h of t is going to decrease. We want to find an expression of how to calculate h as a function of t. Okay, so we're going to rearrange our equations. So phi sub v1 minus h rho g over rv is equal to cv times dh rho g dt. And then we can rearrange this even further, and then we can basically rearrange this into a differential equation. dH dt plus rho g over a rv, a is a cross-sectional area, h is equal to phi v1 over a. Now, you'll notice here that we don't have explicitly phi sub v2, but we have phi sub v2 in the second term of the differential equation with respect to resistance. So remember that the valve on the bottom represented the resistance of the fluid leaving. So it's contained, but it's in this expression, but it's hidden underneath this h rho g divided by a rv, and that's our phi sub v2. So then if we solve our differential equation, and you will see that we can just come up with a standard type of exponential function. H of t is equal to h0 minus phi sub v1 over rv over rho g is an exponential function. And then we have this plus phi sub v1 rv over rho g. And this is basically our starting condition. And then h at times 0 is equal to this h0. So we can use these components as lumped elements if things are flowing in the right way, and if we can assume laminar flow inside these little tubes, then we can do quite a nice little job of modeling these hydraulic systems using the same lumped modeling techniques that we've seen throughout the course. Now I'll talk about flow sensors. There are many sensors that can measure flow by determining the rate of displacement of either mass or volume. So we have mass flow and volume flow. And I will talk about 4 different types today. The Coriolis flow meter, a thermal mass flow meter or measurement, a differential meter, and an electromagnetic flow meter. Now, the Coriolis flow meter, you can read about this, but essentially, remember that we had the Coriolis effect with the bicycle wheel, right? So in this case, you can read about this, but essentially what happens is that a curved tube, a tube that's curved into a U shape, this flow is put through this tube, and when the flow goes through this tube at a certain speed, let's say, it's going to create, again, this Coriolis force on the tube, and it's going to bend it and displace it. So you're going to get opposing forces. If we look at the next slide, you can see this on the bottom picture. Okay. These can also be vibrating tubes. Okay. Now, a mass flow is determined based on the action of the fluid on these vibrating tubes. As the fluid moves from the inlet to the outlet, it develops different forces depending on the acceleration in the tubes. So the force that moves in these 2 directions is going to be 2 times mass times the omega is the speed, or the frequency, times the velocity of the moving, the average fluid velocity. Okay, and then we can measure this deflection of the tubes, or other electrical properties as we do these measurements. Or not electrical properties, but the properties transduced into an electrical measurement. These tubes can be very precise. However, these tubes are very expensive in order to be able to resolve the measurements of the vibrating tubes. And there are many different shapes depending on how you want to do this. You can read more about this in the lecture, I'm sorry, in the textbook, to get a better idea of how these work. Now, thermal mass flow measurements, these are typically used for the measurement of gases, and basically the principal operation is due to a flowing material past a heated element. And we can measure in 2 ways. The first one is we can measure a temperature rise in the flowing material. So you can see the image on the bottom. We have a heater. As the gas passes a heater, it heats up. And then we measure the temperature of the gas downstream at a certain distance. So if you have a certain flow rate, then you can estimate how much it would heat based on the properties of the gas. Or the second way is by measuring the heater power required to achieve a constant set temperature of the flowing material. So anything flowing past a particular sensor is going to have a cooling effect. So in order to get a certain temperature, you have to heat it to a certain level, and then the power that goes into the heater, you can use a calibration to determine this. Now, a thermo-anemometer is composed of 3 small tubes involved, immersed into a moving medium. 2 tubes contain temperature sensors, R0 and RS, and you can see these on the bottom. And you can read a little bit more about these in the textbook and read them. But essentially 2 ways to do the measurement. Now, these are for gas measurements. They're very inexpensive, but they have a limited range of temperatures that you can, of flow rates that you can detect. So you can't do really, really low measurement, really, really low flow velocities, or really, really high or large flow rates. So this slide shows a little bit more about read about the more details of doing these 2 types of measurements using this thermal mass. But essentially, a gas has a thermal mass. You put energy into the gas, and then you basically measure, based on the gas and the temperature and the flow rate, how much heat is being dissipated into the environment, and then you can determine what the flow rate is. Okay. And in order to estimate this, you can use the King's law. So the change in the flow rate with respect to the temperature, and then it depends also on the shape. So for a cylindrical sensor, then the velocity is equal to K over rho times the quantity raised to the 1.87 dq dt, which is the dissipated heat, divided by the temperature. Now, as with most of the sensors, K in this case is a calibration constant, so these types of systems, depending also on the gas, the temperatures you're using, you have to calibrate it. And it's very sensitive to heat dissipation, dq dt. So these are some characteristic curves of the thermal flow, thermal mass flow measurements. And you can see here, again, we can use these elements into a bridge configuration. So we can do these null types of measurements, which is quite nice. So you can look a little bit over the flow velocity characteristics at different temperatures. You can see it can be quite nonlinear, it can be a little complicated. Calibration is absolutely required with these types of sensors. They can be quite useful because of their low cost, but you have to use them over a limited range, and they have to be well calibrated for the particular gas that you want to detect. Now, another way to measure is to use a differential pressure meter. And essentially, these involve the insertion of some device into a fluid pipe that causes an obstruction or creates a pressure difference. These are also called obstruction type meters or flow striction meters. These are inexpensive, very simple, and they can be quite effective, except that you have to, the only problem with these is that you do have to insert some constriction in the flow, and this is not always the easiest thing to do, but if you're doing this beforehand, it can be quite an effective way to measure the flow velocity, because essentially you're just measuring Ohm's law due to this delta P. However, if we have incompressible medium, then we have to use Bernoulli's equation, and then the estimation of the average flow velocity becomes a little more complex. Okay, so the pressure gradient technique essentially requires the introduction of a flow resistance, and then we measure the pressure gradients across a known resistor to calculate a flow rate. So this is, as I said earlier, this is similar to or analogous to Ohm's law. Now there are two types of these differential pressure meters that I'll talk about. On the right bottom image is a porous plug that restricts the flow rate, and on the left we have a constriction type. And in both cases we can introduce an average flow velocity, and you can read a little bit more about these specific cases. The last flow meter I will talk about today is an electromagnetic flow meter. This is quite interesting. It's limited to fluids that are electively conductive. Obviously, we're going to use electromagnetic fields, so we have to have some sort of charged entities in order to be able to detect them. Now, by Faraday's law of electromagnetic induction, so we know this, the voltage E induced across the length of a flowing fluid moving at a velocity v and a magnetic field of flux density B is given by E is equal to BLV. Okay, this is our this comes from Faraday's law of electromagnetic induction. And quite interestingly, this is not so different than the induction law that we use in the homework number 8 for a vibrating wire. So L is the distance between the electrodes and B is known. B is applied to the system. The measurement of voltage E across the electrodes allows the velocity V to be calculated or estimated. Okay. Now, there are two general ways to do this. We can do this in the naive way, where we use a DC method. However, typically, if you use a DC method, like most methods, is that you tend to pick up low frequency noise. And this is problematic in most measurements. So what we can do then is we can go to an AC type of measurement, where we typically can reduce the effect of low frequency noise. And this is a case where we can do an AC type of measurement, and the circuit is located on the bottom. In this case, the frequency of the magnetic field should meet the condition of the Nyquist rate. And you all know this from our sampling lectures, that it must be at least 2 times higher than the highest frequency of flow rate. That is the end of lecture number 9. One more lecture to go, and Meettechniek 2014 will be over. Thank you.